Okay, so our seminar today is by Brenden Epps, who's one of our faculty here. He's going to talk about rapid simulation of fluid energy systems to enable optimization and design. Brenden obtained his bachelor's degree in mechanical engineering from Carnegie Mellon University, and he has an MS, PhD, and he did a postdoc from MIT. So please welcome Brenden Epps.
All right, well, thanks, Ian, for the introduction. Thanks, everybody, for coming. So my title of my talk is a bit of a mouthful. Let's try to digest it. So I'm interested in rapid simulation. I'm a little bit of an impatient guy. I like to get my answers right now. So I like to do things fast. I work in this area of fluid mechanics intersecting with energy systems. So doing things such as hydrokinetic turbines or efficient propulsion systems would be examples of that research space. And then by doing these rapid simulation tools, we really enable doing design work where you want to have an answer within minutes so you can make changes and see what would be the best, most optimized design. So this is kind of overview of where I come from and what my interests lie in. So how I intersected the Thayer School, again, I have a fluid energy laboratory. We're doing things at the cross-section of energy in that research cluster for the Thayer School, and then servicing the mechanical engineering academic disciplines, so teaching the fluid mechanics courses here. I don't know how much we can go further, but we can try. This is not a very bright projector, so I apologize for that. So are we good in the dark? You want to go one up from here? We're good? Okay. All right. So like I said, I teach courses in fluid mechanics, and in particular, I won't be able to talking so much about teaching today. I just want to mention, some of the things I do. So we developed this aircraft design course where students design, build, and fly remote control aircraft to achieve some mission that we set out in the beginning of the term. In the undergrad fluids class, we've done a lot of work revamping all the laboratory exercises for the school. So we made a new lab on airfoil design where the students design and build and test airfoil in our little wind tunnel in the lab. They also do computational fluid dynamics analysis and particle image velocimetry experiments, some of which the same kinds of techniques I'll show you in the talk today in my research. Okay. My research maybe can characterize that based on intersection of applications and research tools. So the applications I'm interested in are things like axial flow turbo machines, such as marine propellers. Cross-flow turbo machines will be the subject of the first half of the talk today. So that's a propeller or a turbine where the flow goes across the axis of rotation, not along through the axis. Unsteady hydrodynamics is kind of the fundamental theory underlying all these things. And so that's one area I work in. And then biomass energy is something I won't be able to talk on today, but it's kind of illustrated here in the middle. This is some collaborative work with Lee Lind and his group where we're trying to convert corn into useful ethanol fuel. And so anytime you're doing any kind of process like that, there's always material handling issues. You want to know what's the material properties of this stuff during this conversion process. And so this year I've become a rheologist. And I have a fantastic grad student who's been working with me on this, trying to characterize the rheological properties of these corn stover slurries. So that's just one example of a collaborative effort that I was really excited about doing when I first joined the faculty here. So I'm really excited at working with Lee on that project, although I won't have time to talk about it today. What I will talk about is some of this work with the cross-flow turbines, illustrated here on the left-hand side of the slide, and we'll talk about low-order model development and validation using computational fluid dynamics in experiment. Okay. So like I said, I'm really interested in design. So the key component of my work is using low-order modeling to create design codes. One example of that is this open prop code. Here's just screenshots of maybe a design and the performance curves you'd get out of my code. The idea behind this is you want to be able to do a design, build, and test all within a day's time. So that was our original concept, and so we have all the tools needed to do that kind of design built into the software package that I wrote. Okay. This has been really successful. It's been downloaded over 5,000 times by people all around the world. I hope to someday write a research article that gets cited 5,000 times, but even if that doesn't happen, I'm really happy to have the codes be used that much. So the OpenProp is just one example of a suite of codes that I've developed. Today I'm going to talk about the CyROD code. I hope to publish all those on the Thayer School website and track all their downloads going forward. In addition to this low-order modeling work, I also do kind of full-blown computational fluid dynamics using tools such as Fluent, OpenFOAM, and Numerical. So whatever suits the need of the project is really what I'm interested in doing. All right, so I'm going to tell you 4 stories today. The first 2 are really in the development of this Thayer code for propeller and turbine design. And then the 2 other stories involve are kind of fundamental things related to low-order modeling. So I'll be talking about the singular value decomposition, which is a way to do reducing the complexity of a model. And then I'll talk about turbulence modeling. So let's just get started with the first story. So first story is to do with marine shipping. So this is the setting. The problem is that fuel accounts for a huge amount of the cost of marine shipping, 40% of the cost of shipping. 80% of trade goes by sea, so anything you've touched or used today probably was on a ship at one point. And if we could reduce the cost of shipping by making propulsion systems more efficient, then that would have a big impact in overall global economics and reducing CO2 emissions. So the idea that we're looking into in this project is one where maybe using a cross-flow propeller could make these types of ships more efficient. And the idea is that given a certain package space underneath a ship, if you have an axial flow propeller, you really only have a circular area that you can capture the fluid, whereas if you use this cross-flow propeller, you have maybe the whole rectangular package space you can use, and if you capture more area, then you could have a more efficient machine. Okay, so that's the theory we're trying to test. So just to give you an overview of the project, we won't have time to go through all the details. In particular, I'm going to skip all the details of the experiment just to say we did that, and I want to give my appreciation to the UNH folks who let us use their towing tank down there. So thank you to UNH. So again, the theory there is you have some package space underneath the ship. If you use screw propellers, you only can capture some of the area. If we use the cross-flow propeller, maybe we can capture more area and therefore have a more efficient propeller. So we're going to focus on this low-order model we made for this system. So if you do any low-order modeling work, you should always think about this kind of space. You always have a trade-off between accuracy and computational cost. The most efficient thing you can do is guess, and it takes no time at all, but you're probably not going to be very accurate. Okay? On the other extreme, you could do what's called direct numerical simulation. You solve the exact partial differential equations which describe fluid flows, and you do that on a very fine resolution computational mesh. Unfortunately, in order to resolve all of the vortices on all of the scales at a flow of this size and speed, it would take lifetimes to compute. You just can't do it for something with this size and speed of such a ship. So in order to make this tractable, people do various things for turbulence modeling. So turbulence modeling is really the art of how do you take DNS and make it faster. And so large eddy simulation or Reynolds average Navier-Stokes are 2 different ways you could do that. What we wanted to do is do low-order modeling. We wanted to go even faster. So looking at some of the options that exist in the literature, we chose a lumped airfoil method because that's really the lowest order method you can get, but still involves some of the physics of what's going on with the airfoils themselves. Okay, so here's just a kind of a sketch of the model. So it's a lumped airfoil method because we're lumping each of these airfoils just into one point vortex. And as the strength of that vortex changes over time, you need to shed a vortex into the wake in order to conserve the total circulation in the whole flow field. Okay? So we have vortices being shed into the wake, and then down here at the bottom, you can see vortices being shed from the leading edge. That's when the airfoils stall. And so capturing that stall behavior with those vortices was another aspect of the model. These arrows represent the forces. You can see the thrust being generated on the upstroke, and then here on the downstroke, and then when it's at the bottom and the top, not so much useful thrust. Some of the key model parameters in this are things like the lift and drag coefficient values that we used for the model. So this CL and CD versus alpha. You can see this plot shows some graph of lift coefficient versus angle of attack. And it's plotted versus various Reynolds number. We talk about Reynolds number in class. It's really like a non-dimensional speed of the airflow, let's say. Okay, so the method for calculating the angle of attack is really important. So that's going to say where you are on this curve. The method of getting the Reynolds number is going to say which curve you're on. So all those things play into doing this calculation accurately. There's some other things that are really important too, but you can go to the papers if you want to see all the details. Okay, so just to skip to the results. Fortunately for us, these model results compared really well to the experiment. surprisingly well to be frank. So here's thrust and side force compared between the experiment and the model. We're showing different what's called advanced coefficients here. So that's a different way of non-dimensionalizing your flow speed by your rotation speed and the radius of the propeller. And so you can see the good agreement there. In this right-hand side graph, we're plotting propeller efficiency versus thrust coefficient. And the spread in the experimental data is a little bit more because for efficiency, you're dividing one measured quantity by another, so you get a little bit more spread in the data. But if you do a curve fit of the experimental data, that curve fit agrees reasonably well with the efficiencies predicted by the low-order model. Okay, so now we can really assess if this is any good or not. So let's take a look. Let's have a little bit of a thought experiment. So the thought experiment is this. If you're given a certain ship, you know the thrust of the ship needs to go a certain speed u, and maybe you know the capture area of a screw propeller you might design. So supposing that ratio turns out to be 1.5, then the efficiency of a typical screw propeller, that's this curve here, would be whatever this value is here. Now, if we could capture twice the area using a cross-flow propeller, then that would knock our thrust coefficient down in half, and we could get maybe marginally more efficient. But I think you can see lots of other scenarios on here. So if your thrust coefficient was 0.5 for the screw propeller, and then you knock it down to 0.25, then you didn't really gain anything. There's lots of scenarios here where the screw propeller is just going to win out. So this cross-flow propeller turns out to not be the best idea, but that's okay. We can move forward with our lives now. We didn't waste lifetimes trying to do the direct numerical simulation because we could do the low-order model and find out the answer a lot faster. The other thing that low-order modeling gives for us is insight into the physics, and it really actually helps us to understand why things are really efficient or maybe not so efficient. And so here's an example. So considering this this rotor, remember this is kind of rotating around as it goes. And if we look at when is it producing lift and when is it really not producing useful lift and thrust. On the top here, the airflow is advancing straight over to the left. The free stream is coming from left to right. So the net inflow is this purple vector here, and any lift is going to be perpendicular to that. That's just going to produce a side force. That's not going to be useful for us at all. In fact, if there's any drag on this airflow, it's just going to knock us backwards. And this is really not useful at all for us. The useful thrust comes from the component of lift when you're heaving either downwards here or when you're going up on this part here. So really, it's the downstroke and the upstroke which give you your useful thrust, and the forward and aft sections of this orbit are not useful at all. So that insight would tell us, hey, why don't we abandon this cross-flow rotor thing and instead look at tandem flapping foils? So if we have a tandem flapping foil situation, then we can produce that useful thrust. And what we could do is we could do it in such a way that maybe the aft foil is going up while the forward foil is going down, and maybe we can cancel out the side forces and have a nice smooth ride going forwards. Okay? So we looked into this, and actually we coined a new non-dimensional number. We love non-dimensional numbers in fluid mechanics, and it's a pleasure when you ever can think of a new one. So in this scenario, the new non-dimensional number we came up with is this non-dimensional blade spacing. So it's the spacing here divided by the distance that these vortices would travel, so in one flapping period. So tau being the flapping period times the free stream would be approximately the distance that the vortices shed from the first foil are going to go in a flapping period. So knowing that non-dimensional number, you can then tune maybe the phase lag of this foil such that it comes up and intercepts those vortices in just the right timing so it can have constructive interference and improve the efficiency of this aft foil. But what I just said is that you would like to have maybe 180 degrees out of phase in order to cancel out your side force. So you could put those two ideas together, and this is where we get on this next slide. So again, we could. So what we did was we did some large eddy simulations, so highly detailed simulations of tandem flapping foils, and we plotted the results here for the thrust and the side force for the forward foil, the aft foil, and then the sum of the two. So the sum of the two is in black, and you see if you go 180 degrees out of phase, then although you get lots of thrust variation, you can cancel out the side force and have very little side force in total. So the black line is almost zero here. If you go 90 degrees out of phase, so one is kind of following each other like this, you could smooth out the variation in thrust. So you see low thrust variation here, but at a price of a high side force variation. And then maybe you can make a compromise in the middle. So, okay, so let's put this all together. You might say, okay, I would like to have 180 degrees out of phase, so I have low side force variation, but then I want to figure out what's the optimum spacing so I get the best efficiency. So using this non-dimensional number, we can come over to this graph here, which plots the contours of thrust, so essentially contours of efficiency, versus the phase angle and this non-dimensional number. And what you see is for a phase angle of pi, we need so much spacing in order to be on this peak thrust zone. So that was another paper we did, kind of saying how would you design such a flapping foil, tandem flapping foil system. Okay. So we started in one realm, we ended up in another, by insights using this low order modeling. All right, let's move on. We're going to change gears now. We're going to go to turbine design. The setting here is marine hydrokinetic energy. The problem is that the levelized cost of energy is way too high for marine hydrokinetic. 21 cents per kilowatt hour is about 4 or 5 times that of wind and coal. So we really need to make this a lot cheaper to be cost competitive on a level playing field. Okay, so the idea is that maybe we can reduce or eliminate some of the expensive equipment needed to install these things. You can see this barge and this crane here used to install this offshore marine hydrokinetic turbine out in this estuary. Those are really expensive pieces of equipment. If somehow we can make this thing act like a propeller, such as the propellers from the previous slides, and then self-propel itself out to the installation site, then we could eliminate the cost of those heavy lift assets. Okay, so what we want to do is be able to design such a things. We're going to try to do this low order modeling again. What we ended up doing was we tried to use that SCIROD 1 code, that lumped airflow method, to analyze the turbines. We found it didn't actually work that well, and we could identify a couple of the reasons why. So a couple of the reasons why it doesn't work well is that the angle of attack is actually arbitrary. It's a little bit ill-defined. You could try to compute the angle of attack at the quarter chord here, or the 3/4 chord, maybe somewhere in the middle. And what you find is that you get 3 pretty different results, and you're going to get 3 different results for the power output of such a turbine. And so with that and a couple other reasons here why this is not such a good method, we decided let's try something different. Let's try something new. Again, we didn't want to go too far over in this cost and complexity map. We said, well, panel methods might be good, but they're not going to really be such a big cost savings over RANs. Let's try something less costly. Let's try this vortex lattice method. One issue is that nobody had ever tried this before for this cycloidal turbine problem. So it was a little bit of an open question. Is this going to work at all? But it's research. It's okay. Let's try it. The other problem with this kind of vortex lattice method is the classical method is actually totally inviscid. It doesn't have any idea of what's going on with viscous effects in the boundary layer. And in particular, here I'm showing just one snapshot in time where the boundary layer is separating here. So this is a plot of vorticity, and where this vorticity gets really thick here is a place where this standard vortex lattice method breaks down. Okay, so we need a way to account for that flow separation. And then what we're going to do is we're going to do what I call viscous thickness load coupling. So in this viscous thickness load coupling, the scheme is to try to account for this trailing edge flow separation by allowing some of the flow to actually bleed through the airfoil. The standard vortex lattice method will essentially solve for the strengths of all those bound vortices in order to have the flow be tangent to the mean line of the airfoil. So which is reasonable because it's a solid body, you don't want to have any flow going through it. But what we found is that we can be a lot more accurate if we actually allow some of the flow to bleed through. And that's reasonable because when you have the flow separation, the flow is not really tangent to the mean line, it's really tangent to the middle distance between the top and bottoms of the 2 boundary layers. And so here in this top plot, I'm showing an example here of a boundary layer plot from a code called XFoil. XFoil is a very well-known panel method which can account for the viscous effects such as these boundary layers. And so using XFoil, we can compute the pressure distribution on this particular airfoil with and without this viscous effects. Okay, so without the viscous effects, we get inviscid predictions by XFoil agree really well with the standard vortex lattice method. And then with viscous effects, you can see the pressure distribution is very much different. With my VTLC algorithm, we can then match this pressure distribution really well, and hence we're going to match the lift and the the moment on that airflow really well as well. The way, if you want to crack open the hood and see how this works, the way we're going to do this is represent that bleed-through velocity and also the source strengths in this vortex lattice method parametrically. We're going to do that using B-spline curves. And the B-spline amplitudes we're going to tune in order to match this orange curve to the black X-flow curve. Okay, so you have to do a nonlinear optimization to solve for those amplitudes in order to essentially trick the vortex lattice method into giving this correct answer. So you build a database of those amplitudes, and then during the turbine analysis runtime, during that CIROD code runtime, we just have to query that database in order to give the right corrections to make the CIROD code act like a viscous code. All right. So this is the theory. We need to test it versus something. Last talk we tested it versus experiment. This time let's do it versus CFD. So here's an example of the CFD Mesh. So this is made by one of my graduate students. And so here's a picture of the overall mesh. This is a zone which rotates with the rotor, and then each zone in here is going to rotate with the pitch of the blades themselves. So you can affect these rotations using what's called non-conformal sliding interfaces. This is a built-in function in Fluent, makes it nice and easy. Well, at least I can say it's nice and easy because my grad student did the whole thing, right? So thanks to Bernie. All right, so here's some of Bernie's results. So again, we're plotting the vorticity fields. On the left is Bernie's results in Fluent. On the right is his model results using the CIROD code. The vorticity is a measure of how much the fluid is circulating around a point. So whenever you see red dots or red patches here, that means the fluid's circulating in a counterclockwise sense. And you can see them kind of rolling up in a counterclockwise way. And then here where you see the blue ones, then it's flow going in a kind of a clockwise sense. You can see that clockwise circulation there. So you have a turbine case on the top, good qualitative agreement between those two cases. Propeller case on the bottom, again, good qualitative agreement in both this, kind of the strengths and the geometry of this flow field. We can overlay these. I love this slide. So we can overlay the two and see a really good agreement. So I thought that was beautiful when Bernie first showed me. All right, so okay, here's some results. Looking at the chordwise force on one of the blades versus the orbit angle, we're plotting lots of things here. The black curve are Rand's results by a code called Overrel. That was by our collaborators at Penn State. The red dashed line are results from Fluent, from our model. So those agree well. Those are both Rand's codes, so they should give basically the same answer. There's 4 low-order models here. The gray dashed line is this code called Cactus, which was made by Sandia National Labs. That's a lumped airflow method. You can see it's not doing all that great of a job. The blue dot dash line was our CIROD 1 code. That was also a lumped airflow code. That's also not doing a great job. The green is the CIROD 2 vortex lattice method without the viscous corrections. And then the orange is with the viscous corrections. So you can see the CIROD 2 with the viscous corrections does a really good job in capturing the total, the chordwise force on one blade and then the total power from all the blades. This is kind of 3 humps per rotation because there's 3 blades in that turbine. All right. So it's more, if you look at the total iteration time, so what's that computational cost for this good accuracy? It's very low, 30 seconds for the CIROD 2 code, as opposed to about 5 days for Fluent or even a little bit longer for the Overrel code. So we've reduced the computational cost by about 4 orders of magnitude, but we get very accurate results. And so with this, we can now use the CIROD 2 code for doing optimization and design work of these rotors. We could also use it as a basis for doing real-time control, because each time step actually converges faster than real time. All right. So I'm going to switch gears and talk a little bit about some of the fundamental math and theory that would maybe underlie some new low-order modeling. And let's start with this singular value decomposition. All right, so what is it? What's it useful for, and so on? So the singular value decomposition is simply a matrix factorization. Say you have a matrix of data A, and we could format that, conceptualize it as a series of velocity fields. And so each column of A over the D data sites, that would be each velocity component at some point in space. And then each row of the A matrix would be some certain time step. So you take all the data for a certain time step and put it into a row of the A matrix. And then you can do this factorization where you get these temporal modes U. The S's are the scalar amplitude of the modes. And then the V's are the spatial mode shapes. This is akin to doing a Fourier decomposition, except for in a Fourier decomposition, you assume the mode shapes are sinusoids. In a singular value decomposition, you let the decomposition itself choose which mode shapes it thinks is the most efficient representation of your data. Okay? Some people might have heard this just called proper orthogonal decomposition. They're pretty much synonymous. The only thing you have to do is put parentheses around the U and the S, and then you get the POD. Yeah. So the SVD and the POD are used all over fluid mechanics, in particular for low-order modeling and for data regression. And the reason they are is because no other low-rank approximation of the data is going to capture more of the kinetic energy in the data as such a low-rank approximation using the SVD. Okay, so this is really important. And the question I'm interested in is, how does this SVD get messed up if you have experimental error? So if you're an experimentalist and you take some measurements, you want to do the SVD of that, then are your results valid, or how far off from what the truth should be? So we're going to collect some data using this technique called particle image velocimetry. Like I said, we now teach our undergrads how to do this in lab. So this is the setup that they recognize. We have a laser which is going to illuminate a horizontal plane of the fluid. We have the fish swimming through that plane here, and from below, we're looking up from the camera. We're turning all the lights off in lab and sprinkle reflective particles in the water so that we get the starry night sky images. And using the PIV software, we get these vector fields, and again, we're plotting the vorticity. So you can see counterclockwise vortices and clockwise vortices kicked off for the fish's tail. Okay? So I wanted to do the SVD of that. So what I did was I took a moving grid, and I interpolated these data on this grid moving with the fish's tail, so I got this noisy wake data. And then I did this matrix factorization, so then I got these spatial mode shapes, the temporal mode shapes, and the singular values. And I asked the question, which of these modes are corrupted by error? And so 8 years ago, I had done this, and I came up with this hypothesis. It was really a hypothesis at that point. I'll admit that now. So my hypothesis was the modes are minimally affected by measurement error if the root mean square error or value of the modes, which is this, is going to be larger than the RMS measurement error. So we can call that epsilon. So if you put this equal to that, you can solve and say the singular value has to be greater than this threshold in order for the mode to be relatively noise-free. Okay? And so here's that threshold with the error from my data and the number of time steps and data sites from my data. Gives this threshold and says modes 1 through 4 should be good. So sure enough, okay, if you put these 4 modes back together, you can do this rank 4 reconstruction, and you can see it pretty much captures all of the dynamics of the flow. You get these vortices, that the fish kicks off. If you do the rank 10 reconstruction, you pretty much just reintroduce your noise. So I said, okay, that's good enough for paper, but we still have some lingering questions. Oh yeah, and I also validated that a little bit by saying, well, if I smooth out the data, then you can compare the smooth weight data to the rank 4 reconstruction. Looks pretty much the same. And the noise, when you smooth out the noise, it just affects these lower singular values. They go down because there's less noise in those modes. But the first 4 modes, relatively unchanged. Okay, so that was what I did a long time ago. What did I do recently? So I had these lingering questions. This has just always been on the back of my mind. When I first got here, I taught Engines 100's methods in applied math. There was one of the students in there who was really slick, and he wanted to do a project over the summer before he went off to grad school. So I said, okay, Ben, let's look at this problem and see if we can dive into it. And these are the 3 questions. How badly are the modes corrupted by measurement error? Can we infer the measurement error from the data themselves? Because otherwise you have to estimate the epsilon somehow. And then is it possible to filter out the measurement noise and reconstruct a true signal? If we could do all these things, I would think this would be a very powerful tool, useful for lots of different people all over the engineering community. All right. So we made some progress, and this took a couple years to do, but we're finally done with this. So what we did was we said, let's construct some analytic data. So we're going to have a U, S, and V matrices we'll construct analytically. It doesn't really matter what these are, but you can just see they're plotted here in black. So in black, you have the data plotted versus position, animated versus time. Here you have the temporal and spatial mode shapes. Again, the black is the analytic answer. and then the analytic distribution of singular values is in black here. To that analytic data, we can add some Gaussian white noise with a certain error that we know. So we know the noise. We can make measured, quote, measured data. And then we could take the singular value decomposition of that and plot it all in red. So then here's the noisy data, and then here's the noisy singular value decomposition. You can see for modes above my threshold, that they work pretty well. It agrees pretty well with the analytic modes. And for modes that are lower, it becomes noisy. And once you pass these other thresholds, you're pretty much in a state of complete noise. Okay? We did a Monte Carlo simulation. We did 10,000 trials of this, and now I'm plotting the mean and the standard deviations, or maybe it's confidence intervals of these trials. And you can see, again, as we go for lower energy modes, the noise in the data affects those modes more, and then your average mode shapes are pretty much zero because you're averaging out all noise. Okay. All right, so that was what I'd done with Ben. And then using perturbation theory recently, I was able to actually derive the quantity I was interested in, which is the root mean square error expected in the mode. So just to define root mean square error, square root of the mean of summing up of the square of the error between the noisy data and then the analytic data. So it's, what's the error in the mode shape, V? Okay. So from perturbation theory, I was able to derive this formula. It looks a little bit crazy, but you put it in the computer and it's easy to do. So the only thing is that the lambdas here are the squares of the singular values, but everything else, okay, it's sums and products and so on. So the cool thing, though, is that using this formula, if the modes are actually well separated, so the S is all fairly distinct, then the summation goes away, and you get this actually pretty simple formula, which is simple enough to be used as a back-of-the-envelope assessment of your modes. I would hope that you could remember this if you cared about doing such a thing. And actually, using this formula, you could evaluate this criterion. If the singular value is greater than this amount, then that ensures that the RMS value is going to be less than this 1 over the square root of the number of time steps times the number of data sites. And that value is going to be pretty small if you have a lot of data that's well resolved in time and space. Okay? So here I'm just plotting this example. So this is predicting as S, for this example, varies linearly with mode K. That's going to make a straight line here. So this works out really well. We also tried it out for other kinds of more complicated scenarios, and it works really well too. But maybe you have to use the full formula some of the times. After you get lower than this threshold, this L2 norm of the error matrix, then you pretty much saturate out to complete random noise. Okay? So using those results, we can then assess how good the mode shapes really are. So the expected value for the noisy mode shape, what we find using perturbation theory, is actually it should be, on average, in the direction of the original mode shape, but because of the noise and the way that these mode shapes are scaled, what happens is your average, your expected value actually decays down to 0. So once you have all noise, you're going to average out all noise and average out to 0. But when you have a low RMS because you have a high singular value, then your mode shape is tracking the analytic one really well. So now we pretty much know how these mode shapes are affected by the noise. And we can use this now in order to reconstruct our data. So there's two other questions. Can we infer the measurement error, and can we filter out the noise? So we can do this in the following way. So again, looking at the plots of the singular values, we see singular values are pretty much unaffected if they're above that threshold. For the low ones, they follow what's called the Marchenko-Pasteur distribution. So what you can do is you can fit this Marchenko-Pasteur distribution to the tail end of these singular values, and where this deviates, that's just about this epsilon times square root d. So you can set that equal to the value of your Marchenko-Pasteur distribution, and you can solve for your error estimate. Okay? So knowing that, you can use this formula then to back out what you estimate to be the true singular values. So you can take these red dots and make them lay back down onto the black curve where they should be. So again, I don't have time to derive that, but that's in the paper. And then using the result on the previous slide, we can say, well, on average, the modes have to be going in the same direction as the analytic ones. So we're just going to take the estimate of the true modes to be what we had gotten from the measured ones. That's the best we can do. We have no clue as to a better direction to go. So using these as our reconstruction, we could then reconstruct the true data, okay? And we'd have used S to estimate the RMS error of that reconstruction. So I think this could be really, useful for things all across engineering. So I'd be really interested to try this out for, say, denoising of MRI images, for instance. Any kind of data regression really is a target for this kind of a process. Pattern recognition, such as facial recognition, is another place where the singular value decomposition is used. And I guess if anybody has like an error in their face, then we could assess that. And then low order modeling again. So that's, I think, something that could be useful to a broad audience here in engineering school. All right, one more story to do with low order modeling. Again, you can't do direct numerical simulation, too expensive, it takes lifetimes. You have to do some kind of turbulence modeling to make a low order model so we can solve it faster and get answers within our lifetimes. All right, so we're gonna do something really crazy. We're gonna take a wildly different approach than what people have done before to do turbulence modeling. And the kind of, aside from the low order modeling angle, the other motivation we have for this work is one purely academic. And the question is it possible to theoretically predict a numeric value for what's called the von Karman constant? And von Karman constant occurs in lots of different fluid flows, but I'm illustrating what's called a boundary layer flow over a flat plate. So say you have a uniform flow, and then it encounters a flat surface here. The flow is going to stick to the surface, but it still wants to go this free stream speed a little bit away from the wall, so you get what's called the boundary layer. And this boundary layer might be on the order of like millimeters on the hood of your car. Okay, so it's really thin where the flow is stuck to the surface of your car, and then it's going the free stream speed just millimeters away. Okay, so you have this velocity profile, which describes that boundary layer. Okay. And it turns out that this velocity profile is logarithmic, and the von Karman constant kappa describes the shape of that profile. No turbulence model to date can predict the value of kappa. In fact, it's the opposite. There's various knobs in all turbulence models, and the kappa in this law of the wall, it's called, is used to tune various turbulence models. Okay? So we get the value of kappa from doing experiments. Here's various different experiments, and you can see if the velocity profile is plotted in the correct way according to this formula, it all collapses to a nice uniform, it's like a universal curve. So we want to see, is there a way we can predict this universal curve from theory, from scratch, from our heads? Okay? So we're going to use kinetic theory to do that. And the starting point we're going to take is this idea of diffusion. In this case, momentum is diffusing away from the wall, and it's diffusing at a certain rate. So in class, we talked about diffusion today. We talked about things scaling, like diffusion happening over certain time scales. And what you find is that diffusion will occur over some distance. So this is units of meters, and that's going to scale like kinematic viscosity times time to the 1/2 power. So if you work out all the units on the right-hand side, this has units of meters as well. So that's the scaling at which the momentum diffuses away from the wall in a laminar flow, in a slow flow situation. In a relatively fast turbulent flow situation where we have these logarithmic profiles, actually you find that the momentum diffuses linearly with time, or linearly with distance down the plate. So according to that. You can see here a smoke plume from Mount Etna. You can see the diffusion happening linearly with distance downstream. And then there's a really famous paper from the 1920s where Richard had showed that particles in the atmosphere disperse like time to the 3/2 power. So there's various physical processes which give rise to various scalings in time, but we could say in a general case, diffusion happens with some physical quantity times time to the 1/alpha power, where alpha characterizes the rate of this diffusion. Okay. So we want to we're going to put that on the shelf now and then think about this kinetic theory framework. So here we want to think about the velocity field as being a random variable. We're going to think about maybe the concentration of smoke as being a random variable as well. So let's let U be the velocity field. Let's let that be a random variable. Let's let C be the concentration of the smoke at some location. And we're going to tag this C as being concentration of smoke at this position in time and space and with particles that have this particular flow speed, U. So if we want to find the total average concentration at that point, we're going to have to average over all the speeds that might be occurring at that point. So we're in this probability framework. So It makes things more difficult in one sense, but in another sense it makes it more easy. So in the easy sense is we have a simple transport by purely advection with no sources and sinks, aside from right there where that is. But down here there's no sources and sinks, so this equation is valid. So the solution is really easy. It says the concentration at some time later is going to be the concentration earlier, but at some upstream position. So that's for the probability space. Now, if we want to look at what's the ensemble average behavior of this, we're going to have to do a little bit of work. So we can say the ensemble average concentration that you would actually observe would be the weighted average over all the different C's for all the different speeds U weighted by their probabilities. If we want to actually say what's the ensemble average transport behavior, so what's the governing equation governing this transport of these things, what we're going to do, we're going to build this equation using this formula. But before we do that, we're going to just start with a simple definition of a time derivative just from high school calculus class or from Math 3. So time derivative is how is C changing with time, divide by t, limit as t goes to 0. So we're going to take this, plug in our formula here for these C bars to now get this really uncomfortable expression given as these concentrations weighted by their probabilities. And what we want to do now is try to somehow impress upon this structure the macroscopic diffusion scaling of interest. So, if we want diffusion to happen along this scaling, we need to somehow impress upon that into this probability distribution. And the way we're going to do that, if we take 150, we think about things such as similarity solutions. And with similarity solution is really how you describe those boundary layers. And so it's natural to use the idea of a similarity solution in describing this probability phase space behavior. So we're going to do that. We're going to say we can define a similarity variable eta. So the actual distance in physical space has this scaling times a non-dimensional similarity parameter. And we can change a probability in velocity space to a probability in these displacements or a probability in this similarity parameter. And what you find when you work through all the math is that this probability in the similarity parameter, in order for the whole thing to be non-trivial and to give anything of interest, you find this probability has to be what's called a Levy alpha stable distribution given by that formula up there. So that's a really awful formula, but we can just give two examples. One is a normal distribution. So we know what a normal distribution is. That's one example when alpha equals 2. And then another example is what's called a Cauchy distribution. So if alpha is 1, which was the case for the turbulent boundary layer, then you get a relatively simple formula for the probability. And if you plug that into this expression, you do all the math, what you get is a fractional Laplacian as the thing which drives your turbulent dispersion. So what we've derived here is fractional Laplacian as a turbulence model describing turbulent dispersion of some passive scalar quantity, such as concentration of the smoke. To my knowledge, this is the first time that fractional calculus has ever been used to describe turbulence in this way. I think this is a brand new result, and it's very exciting because what we can see is that if you use this, then you can do simulations and actually see that you get a linear growth rate of this kind of jet. So I think I just misspoke a little bit. Benoit had worked on this a while ago, and he proposed this fractional Laplacian. He had proposed it for various reasons. What we did recently is to go through this derivation and really derive it rigorously from first principles all the way to having this as a rigorously derived equation. Okay, so it had been considered in literature before, but never derived in this way. All right. So using this as a framework, we can now attack the problem of modeling fluid flows. So again, we're going to start with the Navier-Stokes equations. This is the governing equation of fluid flows. If you do that and you do some kind of turbulence modeling, you're pretty much following what everybody's done for the last 120 years. So this Reynolds average Navier-Stokes, which we talked about in class today, is really we start with the Navier-Stokes equations. You do something to it, and you end up getting an averaged out equation. So Reynolds had done this, and what he found, what his strategy really was like, let's average the equation, and then we'll try to solve it. And that doesn't work because you end up getting terms in the equation which you have no extra equations to solve for. You have this closure problem where you have more unknowns than you have equations. So our approach is exactly the opposite. We want to solve and then average. So the question is, what do we want to solve? We can't solve Navier-Stokes exactly, because if we could, we'd be millionaires. Literally, it's a clay math problem. But anyway, so what we want to do is solve something else. We want to solve what's called the Boltzmann equation. It looks really similar to what we had done on the previous slide, except for replacing C, concentration of the thing, with F, which is the traditional notation in the Boltzmann literature. So just so I can present this to those people, F is now our probability of the speeds of all of the fluid particles. Okay, so this isn't crazy. It's well known. You can do this thing called the Chapman-Enskog expansion, and you can then go from Boltzmann equation to Navier-Stokes equations. You have this equilibrium distribution here. So if you assume that is a Gaussian distribution, or what's called a Maxwell-Boltzmann distribution, and you use this Chapman-Enskog expansion, you can get from Boltzmann to Navier-Stokes. Everything is on solid ground so far. Okay, so here's our approach. We're going to try to use this exact solution of the Boltzmann equation. So we realize that this equation is actually linear in its unknown F, and so you can use the solution that you might have seen in Engines 22 class. And then if you do an ensemble average of the momentum equation, of the Boltzmann equation, you end up getting the momentum equation. And this is looking a lot like Navier-Stokes, except for the fact that we have this stress term on the right-hand side, which we need to evaluate somehow. So the stress is defined in this way. And what we find is that if you plug in this equilibrium distribution, being a Maxwell-Boltzmann, you can get this term to end up giving you these two terms on the right-hand side. So we're still on really firm footing. This is the basis of one paper we're writing right now. And then the basis of a second paper we have in review right now is this idea of using this Levy-alpha stable distributions. And so if you use FEQ as a Levy-alpha stable distribution, plugged in here, you plug this F in here, and you do about 15 pages of algebra, what you find is that you have a fractional Laplacian as a turbulent force in this momentum equation. So again, this looks a lot like Navier-Stokes, where we have the same left-hand side, we have the pressure and the viscous forcing, but now we have this turbulent forcing, which is described as a fractional Laplacian. So I'll wrap up by giving two examples. So here's a wet flow. Here's a plate which is still on the bottom and a plate that's moving on the top. And the velocity profile in this scenario from the measurements is going to look like this log profile, kind of a symmetric double log profile here. From the theory, if you work out, you take the governing equation, you reduce it down to one-dimensional form, and you discretize it in various ways. Then when you solve that numerically on the computer, you find the black curve, which fits well to the data. And then you can fit that with the log profile, which is this red dash curve. So what we're finding is that the fractional Laplacian is going to give us a log profile just as we observe in turbulent flow experiments. We can go back to this boundary layer problem. It's a little bit more complicated. This is a two-dimensional problem. So we have the continuity equation plus the two-dimensional quantum equations. What you find if you go through the math is that this equation is actually parabolic, which means you can solve it numerically using this technique called space marching. And if you do that, and you set this free parameter gamma to 0.192, then this governing equations will give us a turbulent boundary layer profile, which exactly matches the law of the wall. So we're so close. If we could somehow justify this one free parameter, we'd be right there at deriving from scratch the turbulent law of the wall and the von Karman constant. So we're still working on it. We have a couple things to do, but we're really close to having what I think would be a really huge result in turbulence theory. All right, so that's to summarize the talk. We had 4 stories today. We touched on rapid design codes, which is an interest of mine, applied math and theoretical modeling, 2 of the things I do. We validate all that work using experiments in CFD, and it's all kind of in this vein of rapid simulation for fluid energy systems. So with that, I'll take questions and just thank my project sponsors and industry partners, all the students who worked in my lab, especially the grad students who have done a lot of this work, and my collaborators. So thank you.